Hey, it's Mr. Cohen. Hope you're all doing well. And we're going to talk about the rest of Chapter 9, and then we're going to jump back to Chapter 5, and we're going to cover a whole lot of that in this one video. So we're going to start with secant angles, which is the last thing in Chapter 9, or the next to last thing in Chapter 9, actually. Secant angles, now we talked earlier about central angles, which happen in the middle of the circle. We've talked about inscribed angles, which happen on the circle itself. Secant angles happen two ways. They involve lines or line segments or rays, but in the first case, the secant angle is inside the circle, and it's two lines or rays that intersect inside the circle. Now, let's call this angle A and this angle B. Why are angle A and angle B going to be congruent? Because they're vertical angles. Well, angle A intersects this arc over here, and we're going to say that this arc is 50 degrees, and angle B intercepts this arc here that's 20 degrees. Well, to find the measures of angles A and B, we know that they are congruent. We're going to take half of 50 plus 20. So the measure of angle A is half of 50 plus 20, which is half of 70. So angle A and angle B are both 35 degrees. So a secant angle that's inside the circle equals half of the sum of the two arcs, we'll call them arc A and arc B, that they intercept. A secant angle can also happen outside the circle. So here we've got two lines that intersect to the right of the circle as we're looking at it. And let's say that the arc closer is 30 degrees and the further arc is 170 degrees. Again, we've got angle A and angle B that are going to be vertical angles, so they are congruent. But in this case, instead of adding them as we did above, we're actually going to subtract them. The measure of angle A is going to equal half of the further arc, which is 170, minus the closer arc, which is 30. So we have half of 140. The measure of angle A equals 70 degrees. So if we have a secant angle that's outside, we're going to take half of the difference of the further arc, and again, I'm just calling this A and B for convenience, but the further arc minus the nearer arc. Now, moving on. Equations for circles. This is the last part of Chapter 9. The typical equation for a circle is that x squared plus y squared equals r squared. And if you look at the circle here, if the center of the circle is at the origin, the radius equals 5. So we get x squared plus y squared equals 25. And we see that 5, 0 is a point. 5 squared is 25 plus 0 equals 25. 0, 5 is a point, and so on. And if we used Pfag, we would find that 3, 4 is a point, and those all work. So x squared plus y squared equals r squared is the main equation for a circle. But here we've got a circle that's actually centered at 5, 0. If we use x squared plus, and it's the same circle though. I used the cooler that I bring drinks for lunch every day. If we use the same equation, we would find that at a point like 10, 0, it doesn't work. So what we have to do, or 5, 5, what we have to do is we have to adjust for the fact, in this case we moved to the right, we've changed x by 5. So what we're going to do is we're actually going to subtract 5. So that when we get 10, 0, 10 minus 5 equals 5, 5 squared is 25, plus 0 equals 25. 5, 5, we get 0 plus 5 squared equals 25. So it's kind of counterintuitive, but as we move to the right, we're going to subtract from x. If we move to the left, we're going to add to x. If we move up, we're going to subtract from y. And if we move down, we're going to subtract from y. Excuse me. Those are equations for circles. Now, the last thing we're going to talk about in this lesson, we're going to move back to Chapter 5 that we skipped earlier in the year. We talked about some of these things previously because we needed them for Chapter 7. In triangles, we're going to talk about points of concurrency. And if you don't remember, concurrency means that they meet. We're going to talk about 4 different kinds of points of concurrency. The first is called a circumcenter. And a circumcenter is where the perpendicular bisectors are going to meet. So if we drew a perpendicular bisector of this triangle here, we would draw 3 of them. And this point here would be called the circumcenter. And what's important about the circumcenter is that it is equidistant from the vertices. And again, it is made up of perpendicular bisectors. The next one is made up of angle bisectors. So we're going to split this angle in two, we're going to split this angle in two, we're going to split this angle in two, and they meet about there. So these are angle bisectors. And the point of concurrency is called an incenter, which is perfect because it's in the center of the circle. The incenter is equidistant from the three sides. I know if I'm going fast through this, you can always pause and rewind. All right, so we have the circumcenter that's equidistant from the vertices, made up of perpendicular bisectors. We've got the incenter, which is made up of angle bisectors. It's equidistant from the three sides. Our next one is made up of medians. Now, a median bisects a side, but it doesn't automatically bisect it in a perpendicular way. So the bisector for here might be that, and it might be perpendicular. But this one is not perpendicular. This one is not perpendicular. Now, the medians meet at the coolest word in all of geometry. It's called the centroid. Now, the neat part, or the part that you really need to know about the centroid, is that for each of the three line segments, this distance is 2/3 from the vertex to the centroid is 2/3 of the length, and from the centroid to the side is 1/3 of the length. And that will come up in an awful lot of problems. Again, we're looking into chapter 5 now. Now, the last thing that we're going to talk about in this video, this is again at the beginning of chapter 5, is made up of altitudes. And you'll remember that an altitude is a perpendicular to a side. We use altitude to mean height in a lot of cases. And so we're going to draw 3 altitudes here. And what we've created is called an orthocenter. An orthocenter is the point of concurrency for 3 altitudes in a triangle. Now, what's interesting about the orthocenter is, and we talked about this a few months back, is that in some triangles, especially obtuse triangles, orthocenters happen outside of the triangle. In a right triangle, they happen at the vertex of the right angle. So we've talked about circumcenters, incenters, centroids, and orthocenters. That should get you through the start of chapter 5. Now, I want to thank my wife for filming this. I want to thank our dogs for not barking during this. And I want to remind you that if you have any questions, you can email me right here at mcohen2@pghschools.org. Stay safe, and we'll make more of these sometime soon. Bye.